Alright guys, let's get started.
So there's some comments about the homework. Let's go over some of those. Let's basically review and put it in context, that homework question. So last time we talked about confidence intervals. So what was the point of a confidence interval?
Confidence interval, showing the entire problem, shows a percentage of a sample with a degree or margin of error based on confidence level to provide a useful result.
Okay, excellent. So let me describe basically what you said and broaden it out even more. So remember our whole mission was we had some population and we wanted to estimate some true number about that population. So in the example we gave, that true number we wanted to estimate for the population was the percentage that approved of the president. In general, we call that a percentage of success or proportion of success. So we wanted to estimate a proportion of success. In this case, it was the proportion of people who approved of the president. And obviously, success isn't necessarily a good thing, it's just whatever we're keeping track of. And so we said that if we were able to have access to all the data in the population, to get this proportion of success, it would be easy. You just look at every single person and count up all the ones that say, yes, I approve, and then divide by the total. So if you had access to everybody in the population, then it would be easy. But you don't have access to everybody in the population. We said it was infeasible. So instead, we have a sample. And from that sample, it's much smaller, it's much more feasible to collect. And let's say, for example, we have a sample of 100 people, and of those, last time we said 37 people approve. So in this sample, we have 37% approval. So the big question, the $1 million question is, what conclusion can we make for all 300 million people, knowing that of these 100 people, 37% approve? Can we say that exactly 37% of the whole population or the whole country approves of the president? And we said that no, we can't, because this is such a much smaller number compared to the 300 million. So the best we can do is qualitatively say that approximately 37% of the population approve the president. But now it begs the question of what approximately actually means. And that's what we quantify. And so in the end, we can't just say this one number approves of the president for the country, but we say approximately around this number, and the conclusion is in the form of a confidence interval. So the best we can do is say that the true number that approves of the president will be 37% plus or minus some margin of error. And then there's a third number. We say that the true number will lie inside this interval some percentage of the time. So for example, with 95% confidence. So this conclusion is how we specifically quantify what it means to be around this number, 37%. So the true number will be inside this interval, this percentage of the time. And so collectively, we call this a confidence interval. So confidence interval consists of this interval of possible values along with a confidence level. So that's what we talked about last time. Any questions? Okay, so the whole point of confidence interval is to estimate some true number about the population using a sample. So we talked about how, in this case, we're trying to estimate this particular type of number, a proportion of success. So in that case, we have a formula associated with that. And so P is what we're trying to estimate for the population, the proportion of success. P hat is coming straight from the sample. So let's just fill in the numbers. In this case, it'll be 0.37. This Z-score is something that's calculated directly from the confidence level. So again, the confidence level is usually given to you or chosen by you, but ultimately it's chosen by somebody. So it's just a number that's arbitrarily chosen by somebody. The confidence level is arbitrarily chosen by somebody, but the z-score is calculated based on that chosen confidence level. So let's say that the confidence level is given as 95%. This is given. And then we'll talk in more detail how to find this z-score again. We'll review that again. But for now, we'll fill in the rest of the pieces. P hat will be the same P hat as before, 0.37. Q hat will be
0.63.
1 minus P hat, which is 0.63. So that's how you mathematically find Q hat, it's just 1 minus P hat. But conceptually, the meaning of Q hat is the complement of P hat. So P hat represents the proportion of success in the sample. Q hat represents the proportion of non-success in the sample. So if success, in this case, is approving of the president, non-success would be everything left over, either not approving of the president or being indecisive. So proportion of non-success or not approving of the president would be 0.62. And then divided by n, which is 100. Okay, so that's the sample size. So all of this is coming straight from the sample. The only thing that's left now is the z-score. So let's talk more about that. So again, the z-score is determined strictly off the confidence level. The confidence level is given at 95%. So remember we talked last time about this z-score here. It has this alpha over 2 as a subscript to the right of that z-score. So we said that the confidence level given is 95%. Alpha is also called the significance level, and it's everything that remains from this confidence level from 100%. So it's simply 100% minus the 95%. So it'll be 5% is up. And 5% expressed as a number is also 0.05. And then, so we're looking for alpha over 2 as part of this formula. So if alpha in this example is 0.05, then alpha divided by 2 is half of that, half of 0.05, which is 0.025. Or you could have done half of 5%, which is 2.5%, convert to a decimal, is 0.025. So that's alpha over 2, and then if we look collectively at this entire symbol, it's z with this whole thing to the right of it. So alpha over 2 to the right of it. So it's z with 0.025 to the right of it. So we just converted the z alpha over 2 to z with 0.025 to the right of it. So what this means is if you look at the bell curve, we're looking for the z-score that has that much area to the right of it under the bell curve. So the area to the right that we're looking for is 0.025. So we said that there's a table for you, a z-score table, that has a relationship between two things, z-score and the area to the left of the z-score. So if you know one, you can find the other. In this case, we're trying to find the z-score, so if you knew the area to the left of that z-score under the bell curve, then you're able to find it. So the green is the area to the left of the z-score under the bell curve, the black is the area to the right of the z-score. So if you know the area to the right being 0.025, what's the area to the left?
Subtract 0.025 from 1, and it'll give you your answer. And 0.975 equates exactly on the z-score table to 1.96.
Okay, very good. So a right area being 0.025, to get the left area, you subtract from 1, because the total area under the bell curve has to be 1. We said that that's mathematically true. And so subtracting that right area from 1 gives 0.975 as the left area. And so then if you look on the z-score chart, all the numbers in the first column represent z-scores, and all the numbers in the middle of the table represent left areas. So we're looking for left area 0.975, so look in the middle of the chart here, and look for 975. They're in ascending order from top to bottom, left to right. So It'll help you find it, knowing that it's already in order. So look for 0.975, and this number is searched for so often that you'll see this exact number, 0.975. You won't even have to interpolate. And that corresponds to 1.9 over here, and there's gonna be, you're adding in an extra 0.06 in the table. So the total z-score ends up being 1.96 for that particular vector. Any questions? Okay, so that's reviewing how we found that particular z-score for that particular confidence level of 95%. Now the homework is gonna have you practice this, so let's practice it together. So instead of a confidence level of 95%, let's practice with a confidence level of, let's say, 90%. Before we switch confidence levels, let me show you this in a different perspective as well. So the way we found the z-score in the end is basically we did it mechanically. From the confidence level, found alpha over 2, step by step like that. Another way that you could have thought about it is a conception, a more intuitive way. And this actually helps you visualize and understand why we're doing this a little bit more. So you have this bell curve. And so this given confidence level here represents the total area around the mean to be equal to the confidence level of 95%. So this area around the mean is the 95% representing the confidence level. So that means there's these two areas left over that we call the tails of the distribution. Areas that are either too low or too high over here. So let me show you those in. So these shaded extreme areas are called the tails of the distribution. So the right one we call the right tail. Left one is left tail. So again, if you're given a confidence level, visually, that just corresponds to the area around the middle of the distribution with the tails left over, the two tails on both sides. Okay, so both of these boundaries that separate out the tails are going to be data points that have their own z-scores. So there'll be this z-score here and this z-score here. So basically we want to find what those boundaries are. So let's start with the right one. So how would you be able to find this z-score, basically that has this middle area of 95% around it? What must be left over in the right tail for you to have this middle area of 95%?
2.5%.
Yeah, very good, excellent. So if the middle area is 95%, that means there's 5% left over across both tails. So each individual tail must have half of 5%, which is 2.5%. And that's what this alpha over 2 is doing here. And that's what the 2.5% that you calculated before is doing. It's finding the area of one of the tails. So this right tail is going to be 2.5%. This left tail will also be 2.5%. So basically to find the z-score, once you know the area, either to the left or the right, you can find the z-score. So knowing that there's a right area of 2.5%, that means there's a total left area of how much? Relative to the z-score that you're trying to find, what's the total area to the left end of the bell curve?
97.5.
Yeah, you can do it one of several ways. Either add up this middle 95% and then add this left tail of 2.5%, that'll give you the 97.5%. So relative to the z-score you're trying to find, the total area to the left end of the bell curve is the 95 plus 2.5%, or 97.5%. So that's how we're getting the 97.5% that we need to look it up in the table representing a left area to find the corresponding z-score. So another way that you could have done it is the way we did it before, which is this z-score you're trying to find has a total right area of 2.5%. So therefore the left area must be what's left over from 100%, which is 97.5%. So same ultimately, both perspectives lead to the same thing. And ultimately, you're getting a left area of this 97.5% that you're looking at from the chart to get to 1.96. So this is another way that you could think about it, is given this confidence level, that will represent a middle area in the distribution of 95%, and then you're just looking for where this boundary is and the z-score for that boundary. So this z-score, we looked up in the chart to get positive 1.96. So what must be the left of z-score if this one z-score is positive 1.96? So notice that these two boundaries are symmetric, right? And so what that means is that each z-score is the same distance away from the center. And
So 0.02, 0.02.
well, okay, so each z-score is the same distance away from the center, and if the meaning of a z-score is the number of standard deviations away from the center, or away from the mean, then if the right boundary has a z-score of positive 19.96 standard deviations away from the mean, then the left boundary must have a z-score of negative 1.96 from the center. So this boundary is actually the same value, just negative.
Okay, I didn't understand the way you worded it, so I understand what you mean now.
Yep. So, because these two boundaries are basically the same numerical value, just different signs, we only need to look at one of them. And so that's why in this formula, we're only looking for the right boundary. And so we end up looking for this one, 1.96. And that's why the formula, you're adding and subtracting that number from both sides. But we only need to come up with that number once. And then add and subtract that number multiplied by this number of standard deviations on both sides. Any questions? Okay, so the z-score, one way that you can come up with it is strictly mechanical. Start with the confidence level, get alpha over 2, find the z-score that has that much error to the right, and you're done. Another way that you can think about it is visual. The confidence level represents the middle area, and then find this boundary that must have this much area to the right of that boundary. Any questions? Okay, so now that we found the z-score for 95%, let's practice and change the confidence level and find the new z-score. So let's say that the new confidence level is 90%. So let's practice. We're looking for z alpha over 2. So if the confidence level is 90%, what's alpha?
10%.
Yeah, 10%. What's left over? If alpha is 0.1, then what's alpha over 2?
0.05.
Yeah, half of that, 0.05. So now we're looking for the z-score, or the right area of 0.05. If you look at your table, if you look at the distribution, we're looking for the z-score with the right area of 0.05. So to use the chart, if we know the left area, we can find the z-score. So what would the left area be if the right area is 0.05? Yeah, 0.95. So the right area is 0.05, left area is everything from 1. So 1 minus 0.05, 0.95. So now we look at 0.95 in the chart and look for the corresponding left area.
1.645.
Yeah, 0.95 is the left area. We'll give you a z-score of 1.645. This is also a number that's searched for so often that the chart will also give you an exact answer. So, so if the confidence level had been 90%, then the z-score that you would have used for the formula, z alpha over 2, would have been 1.645. So the way that we did it this time was purely mechanical. So the second way that you could have done it is you could have drawn a picture, and the confidence level, let's give it a 90%, represents this middle area of 90%. Now there's 2 tails left over. Those 2 tails add up to what? 10%, so each tail individually is half of 10, which is 5%. So there's 5% on each side. So now we're looking for these two boundaries. And you know that the value of the boundaries will be the same, they'll just be different in signs. So we'll just find the positive boundary. So that'll be the z-score that has this much error to the right of it, which is 5%. And then so same, now it brings us back to what we did before. So look for a left area of 95%. So we'll get the 1.645. Any questions? So you guys feeling good about calculating this z-score for any confidence level now?
As long as they tell me what they want.
Okay.
And I say it that way because they say based on a level with this, is like, calculate it when you don't have any of the information, what you need to be able to find a percentage of the population within this many, with this much percent. That was like one of the questions on the homework last night.
Okay.
So they'll give you an example, it's like do it for 90 or 95 with this much percentage of whatever, but they don't give you any numbers, you're just trying to figure out what you need when you have an unknown thing. It was the one about products. It's like their toothpaste brand, they wanna get it out to everybody, he wants to know how many he has to sample within like 6% to be able to increase his advertisement or make his product better.
Okay. So I'm not sure about that phrasing. We'll have to look at the exact phrasing so that I don't steer you wrong. But yeah, if we look at the exact phrasing, then we can do that one. If you wanna hit on like, ask my instructor, it'll send me that exact question that we talked about in class. Okay.
And so at the end, when we calculate all this stuff, when you go back up to the original equation, since we plugged in everything on one side, what is P? The original.
Yeah, so P will represent some number plus or minus another number. So some number plus or minus another number, so you're gonna get a resulting interval of possible values.
Okay.
So P represents, true number could lie somewhere inside that interval, some percentage of the time corresponding to your confidence level.
So it's almost like your range.
Yeah, exactly, yeah. So this formula is giving you a confidence interval for P, which is what you're trying to estimate for the population. In this case, like the percentage of people who approve the president. So that percentage of people who approve the president will be some number like 37% plus or minus a margin of error. So the thing after the plus or minus is a margin of error. Okay, any questions? All right. Good, that was a good review. So this is the main formula we talked about last time to estimate P, proportion of success in the population. So last time I kind of just gave you this formula and then we just practiced it. And then we talked about when to apply it, but we didn't really talk about where it came from and why you would use this formula. So let's talk about that a little bit today. Give you some insight as to where it's coming from and that it's not just something that's thrown at you that you're expected to just accept. So let's go with the example of let's say that you have a multiple choice test. Of 32 questions. And let's say there are 4 choices per question. And so let's say that you have let's say that you guess on all 32 questions. And let's say that you guess on all 32 questions and you happen to get 10 correct. So on this one particular sample, on this one particular set of 32 questions, you're guessing and you're getting 10 correct. Now you want to know what's the truth for the entire population. If instead of this just one sample where you're getting 10 out of 32 correct, what would be the proportion of success for the entire population if people were, lots of people were to guess on a 32 question multiple choice? So basically, you have the results for a sample, these 32 questions, and you want to know what the truth is for the whole population of possible values. So let's go ahead and use the same formula we've been talking about to get the conclusion in terms of a confidence interval. So in this case, what's p hat?
10.
Yeah. So note that this is p hat, which is the proportion of success in the sample.
Would it not be 10 out of 32?
Yeah, it would be 10 out of 32.
Okay.
Okay. So it would be 10 divided by 32 instead of just 10. So this is the proportion for the whole sample. So assuming the sample has 32 questions, and the proportion of success would be the number of success 10 out of 32. So that'll be plus or minus the z-score, which we'll fill in last. So if p hat is 10 out of 32, what's q hat?
22 out of 32.
Good. So if you get 10 questions right out of 32, you're getting 22 questions wrong. So the proportion of non-success is 22 out of 32. So divided by n, so n will be 32. Okay, so again, we're gonna fill in the z-score, and this is dependent on the confidence level that's given to you. And so let's say the confidence level given to you is, let's say again, 95%. So we're looking for the z-score that has a right area of half the remaining sum of the tails. So the tails sum up to 5%. Each tail will be 2.5%. So we're looking for the z-score of the boundary that has a right area of 2.5% or a left area of 97.5%. So we calculated that yesterday. Right? And if you look at it on the chart, that'll be 1.96. So the z-score will be 1.96. So let's go ahead and calculate this. See what we get. Let's calculate the margin of error first, the thing after the plus or minus. So there's a lot of fractions here, so be careful.
I converted to decimal. I just got a question. How many points do you want? 4, 3,
4 some.
4 corresponding, so I got, 1606. Correction, 0.1606.
Okay, and the 10/32 is roughly 1/3, 0.34 maybe.
If we're doing 4 decimal points, 0.3125.
0.3125, thanks. Okay, so just like before, we're gonna get an interval of possible values where the true proportion of success for all test takers will be inside this interval 95% of the time. So what's the lower bound and upper bound of that interval?
Lower is 0.1519.
Okay,
Roughly upper is 0.4731. 31.
so based on this example, you actually know what the true proportion of success is without even having to do any more math, right? So the true proportion of success, in this case, because there's 4 choices per question, what should be the true proportion of success? If you were to guess on a multiple choice question, then if there's 4 choices per question,
You have a 25% chance of getting it right.
you have a 25%. So the true proportion of success should be 25%. But because there's only 32 questions here, you're not gonna get exactly 25 questions, 25% of the questions right every time. So you'll see some variation here. So 10 out of 32 ends up being 0.15 or 0.3125 instead of exactly 25%. But the question is, we're trying to, from this one sample, get the true proportion of success. And we actually know what the absolute ground truth is. The truth is 0.25, right? But this method, this confidence interval method, gives you an estimation of what that value is in terms of a range of possible values. So we're saying that based on this one sample, we're predicting that the truth is somewhere between 0.15 and 0.47, but we know the truth is 0.25. But the point is that we're getting an estimation of what that true answer is. Any questions? Okay. So along the same lines, if we were to look at a distribution, where we're looking at the number of successes out of 32 questions, so the x variable here represents the number of successes out of n trials, or n in this case is 32. So if you look at that distribution, it's gonna look something like this. You're gonna get a certain number of questions right, with the most likelihood. And then, so in this case, if there are 32 questions, you have 4 choices per question. What is the most number of questions correct that you should get with the most likelihood? What's the number of questions you should get correct with the greatest likelihood? If you were to guess on 32 questions, 4 choices per question. So one time you might get 7 questions right, one time you might get 10 questions right, one time you might get 7 questions right. But if you repeat this lots of times, then the number of questions that you get right by guessing on 32 questions should be what in the end?
Average out to about 8. I believe.
It should be average out to 8. Good. So at 8, this should represent the probability of getting that value, and that'll be indicated with the height of this bar, which is highest compared to all the other possible values. So at 9, if you guess, you could very well get 9 questions right out of 32 questions if you guess. But that's going to appear with slightly less likelihood. And then the same thing for 10 and so on as you move away from 8. And then we see this before. You have this distribution with a whole bunch of gaps in it. And so first of all, this is a kind of discrete distribution because it has all these gaps, because where the gaps are, the probability of getting those values is 0. Because you can't get 7.2 questions right out of 32 questions if you guess. It's only a whole number of questions. But you can actually fit or approximate another distribution to this, and what is it?
A normal distribution?
Yeah, you can fit a normal distribution or a bell curve. But the distribution that you're approximating, being the bell curve, that's only an approximation. The actual distribution, the original distribution, was what kind of distribution? It's discrete, but specifically what kind of discrete?
This is a binomial probability distribution?
Very good, excellent. So the original distribution, recall, was a binomial probability distribution. Because each of these probabilities, i.e. the heights of each of these bars, can be calculated as the probability of this number of successes out of this number of questions. So each of these probabilities are binomial probabilities. They can use that binomial probability formula for the n choose x, p to the x, 1 minus p, then minus x. So this is a binomial probability, and the way that you would calculate the heights of all these bars, or the probabilities at each of these values, would be to use this formula. So therefore, this distribution is a binomial probability distribution, because all these probabilities are binomial probabilities. Any questions? Okay, so in this case, we happen to be in a situation where all we've observed is this one sample of the 10 questions right out of 32. And basically, we want to re-engineer or reconstruct what the original distribution must be that gave rise to this observation. And so, in this case, we're basically working in reverse. The only observation we have is this 10 correct out of 32, which is the peak will now be the 10. And then in order to get the correct population proportion, now we're going to move 2 standard deviations on both sides. And basically these values at the boundaries will end up being the same values that we get in the end in a confidence interval. So essentially that's all we're doing. We're starting with the observation of the sample, and we're just adding and subtracting the margin of error on both sides in order to get these boundaries for the confidence interval that we ended up calculating in our formula. So that was the big picture, so let's actually do that. So the first thing is 95% confidence. You see this on your homework a lot, where basically to find the typical or usual values, you're just starting with the mean, and you're adding 2 standard deviations to the right, and 2 standard deviations to the left. So you're adding 2 standard deviations, and you're subtracting 2 standard deviations from the mean. Now, This too, now you're ready to appreciate, is really just an approximation. So based on 95% confidence, when we actually calculate the z-score to get the boundary around 95%, this z-score is actually not 2 for 95%, it's actually what?
1.9.
1.96. So the 2 that you've been using all along in your homework has been an approximation of the 1.96 that you got from the chart. Okay, any questions? Okay, so we're gonna start at the mean, 10, and we're gonna, for this right boundary, we're gonna add 2 standard deviations. But 2 is just the number of standard deviations. Now we have to multiply by the number of units for each one standard deviation. So basically we have to add the number, multiply this 2 by the number of units for each one standard deviation. So based on this distribution that ended up being a binomial probability distribution, how do we find the number of units in one standard deviation?
Is it the? Doing it the same as the rest of the formula, since we already know what the z-score is? Is it-
Yeah, so what we're doing
P hat
now-
Minus q hat.
Yeah, so what we're doing now is we're basically deriving this formula. So assume this formula doesn't exist for now. So based on what we talked about earlier, based on basic principles, chapter 6, for example, based on the fact that we have a binomial probability distribution, how do we find the mean and how do we find the standard deviation?
So you have to take your probability of possible successes and however many times, and then, multiply that by the probability of failure, however many times, and then divide it by the number of samples.
Okay, so recall that we said that once we're able to pinpoint that we have a binomial probability distribution, finding the mean and standard deviation are simply simple
N
shortcuts.
times p, and then the square root, or sigma is gonna be the square root of p q n.
Very good. So the mean will be simply n times p, which in this case is n is 32. P is proportion of success per question, probability of getting each question right, which is 1/4, because there's 4 choices per question.
So 0.25.
That'd be 1/4, 0.25, so 33 times 0.25, 32 divided by 4 is gonna be 8. So the mean will be 8 here. But in particular, the one we really wanna get is the standard deviation. So what's one standard deviation?
Square root of, p times q times n, so it's normally npq, so I put that down.
Yep, square root of NPQ. And so let's do that together. N is gonna be 32. So notice that the P and the Q are what we actually know is the proportion of success. What we're doing here is that we have this one sample. And from the sample, the proportion of success in the sample is 10 out of 32. So in the sample, proportion of success will be 10 out of 32. So that's what we're gonna be using because we don't know the true P yet. That's what we're trying to find. So right now we're gonna use P hat and Q hat. So P hat will be 10 out of 32. So what will Q hat be?
22 out of 32.
Yeah, 22 out of 30.
It's gonna give you square root of 10.
Square root of 10. Yeah, that's right, because all these things divide out. And so square root of 10 is approximately 1. Well, it should be the square root of 10, because, you have a 22 divided by 32 here, so it'll be a little less than the square root of 10.
The square root is 6.875.
Uh-huh, yep,
And then that
because this is 22 divided by 32.
Yeah, so it's gonna be 2.62.
2.62. And so, actually the mean here is the same thing, because here we're given a sample, we don't yet know the ground truth. So the mean will be the mean from what we see from this sample, which is N 32, P is the proportion of success in sample, which will be 10 out of 32, so the mean will be 10 here. So I want to remind you guys again, what we're doing here is, this part is kind of enrichment. This part is kind of trying to derive this formula that we talked about yesterday. So if this part isn't completely clear, that's okay. But if it is clear, that's even better. So it's trying to get you to internalize and understand where this formula is coming from. But in the end, if you don't understand it, the most important thing is just being able to apply this formula correctly, which is what we did yesterday. Any questions? Okay, so from this one sample, we're trying to get the ground truth of what the proportion of success is for all test takers. So basically we're going to start in the middle here, which is the mean of 10, and then we're going to add and subtract 2 standard deviations, but now we know the 2, based on 95% confidence, is just an approximation. So the 2 is really 1.96. And now we have to multiply by this number, which is simply the square root of NPQ, which is the standard deviation of any binomial distribution. So if you punch this in, punch in the margin of error first, the thing after the plus or minus. Tell us what number you get for 1.96 times 2.62.
5.1352.
5.1352.
Yeah.
So the final number of questions right that you'll get by guessing out of 32 questions will be somewhere between 10 minus 5.13 and 5 plus 5.13. So go ahead and calculate an upper and lower bound for that.
Lower is 4.8648, and upper is 15.1352.
Lower is 4.1 now.
8648.
8648. Okay, so this represents the number of questions you should expect to get right out of 32. If you were to guess, this represents the true number of questions you should expect to get right. But this is just the number of questions correct out of 32. All along, we were trying to find the proportion of success and not just the number of success. So how do you convert a number of success to a proportion of success? If you know that you're going to get somewhere between 4 questions right to 15 correct questions right out of 32, then what's the proportion of success if the numbers are 4 and 15?
Divide each of those numbers by 32.
Divide each of the numbers by 32. Good. So, just to be clear, if you have 32 questions and you get 20 questions right, and I ask you what proportion of questions are you getting right, well, the proportion of questions you're getting right is 20 divided by 32. So the number of questions right is 20, but the proportion of success is 20 divided by 32. So same thing here. The number of questions you're getting right is anywhere from 4 to 15 out of 32 questions, so the proportion of success, we'll divide each of these numbers by 32. So if you do that, you should be getting exactly the same numbers that we got over here, 0.15 to 0.47. So basically we just derived this formula here. Any questions so far? And just to recap, our general steps for deriving this formula, all this formula is, where it's coming from, is that we're starting with what we observed in the sample. So in this case, what we observed in the sample was we got 10 questions right out of 32. So that's where we started, is the 10 out of 32, which is giving us the 0.3125. That's the sample observation. And then we're adding and subtracting the z-score, the number of standard deviations that's corresponding to a certain confidence level. So before on your homework, we've been using 2 all along, but really for 95%, it's exactly 1.96. And then this number here, this is just the standard deviation of any binomial distribution, which is the square root of NPQ. But right now, the only thing we can observe is P and Q from the sample, so we're using P hat, Q hat. But then this is just the standard deviation for the number of successes out of the total. But if we want the standard deviation for the proportion of successes, we're going to divide this number by n. And it turns out if you do some algebra, this is exactly this. These two are exactly the same. And we can actually do that together to show you that they're the same. So we're trying to show that this original standard deviation for any binomial distribution divided by n to get the proportion actually simplifies algebraically to this, the one that's used in the formula. So let's show that. So you know that if you have a number, you can multiply that number by 1 and preserve that number. So let's say that we were to multiply both on the bottom of this fraction by the square root of n. And we're multiplying both the top and the bottom by the same number, so that effectively we're multiplying by 1. We're not changing the value. So if you do that, then what's the bottom become?
N times the square root of n?
Yeah, we're just gonna multiply across, top to top, bottom to bottom. So the bottom, if you multiply across, will be n times the square root of n. Okay, so let's multiply this across. This will be the square root of n times p hat q hat times the square root of n again. So you know that if you multiply two square roots separately, like for example, the square root of 4 times the square root of 16. If you have these two individual square roots, and they're both multiplication, you can actually combine them under one square root with multiplication. So this is the same as the square root of these two individual arguments being multiplied. So this is actually the same. So you can combine these two square roots into one and multiply the individual results. So same thing here, you can combine these two square roots under one, multiply these individual results. So this will be n squared times p hat q hat. And then you also know that if you have a square root with all multiplication like we have here, then this is the same thing as being able to effectively distribute the square root across each term. So this is the same thing as the square root of n squared times the square root of p hat times the square root of q hat. And then divide by n squared of n. And then, but the square root of n squared simplifies to what?
Again,
Just n, okay. N, and then times, let's go ahead and merge these two into one square root, so this will be the square root of p hat q hat divided by n squared of n. So now you have all multiplication and division across these, so you can choose to divide first. We'll divide n by n, so they'll cancel out, and then you'll get square root of p hat q hat divided by the square root of n. So since it's all multiplication and division across these square roots, you can choose to put everything under one square root again. And so this is the final result that we get, and it's the same one that you see from this formula. Okay, so again, all we're doing is deriving this formula and showing you that it's coming from what we've already talked about. Any questions? All right. So what we just talked about was a confidence interval, and remember the whole point of a confidence interval was to estimate some true number for the population using a sample. In this case, the true number we wanted to estimate was p, a proportion of success for the population. Now, there are other numbers that we're interested in estimating, not just a proportion of success. So another example of a number we're interested in is a population mean. So one important thing is I want you to get a feel for what the difference between these two types of numbers are. So, for example, if you have, let's say we had access to all the numbers in the population. So let's say the population happens to be the country. Let's say that somehow you got access to all these numbers. My map just keeps getting worse and worse. But let's say you had access to all these numbers. If you wanted to find the population proportion of success, P, and you got access to all these numbers, what would be the approach that you could take to find the proportion of success if you knew all the numbers? Well, you would look at each number one at a time and see whether it was a success or not. If it was a success, like if they approved of the president, like you would count them. So you would count all the ones that were deemed a success, and after you counted them all, you would divide by the total number of people, or total number of data points, and that would be your proportion of success. So it would just be the number of successes each one was either yes success or no not a success, and then you count all the successes, and then divide by n total. So technically, since this is a population, I'm going to use capital N. So that's if you're trying to find the proportion of success. But what if you had all the numbers in your population and you wanted to find a mean value? For example, a mean IQ score. So then you're going to look at each person, find out what their IQ score is or what their number is, and then you're going to add it to the next person's number, and then the next person's number, and so forth. Add up all the numbers, and then divide by the number of numbers. So that's what we mean by mean value. So the way that so the meaning of these two types of numbers are different. One is a proportion of the number of successes, and one is the average of all the values. So sometimes we might be interested not in a proportion of success in the population, but a mean value in the population. So if we're interested in the mean value of the population, for example, the mean IQ score out of everybody in the country, instead of having to give everybody in the country an IQ score, and take the average, what we'll do is we'll select a much smaller sample of people, give an IQ score to them, a random sample, and then from there, put it into a formula to find a confidence interval of possible values that the actual average IQ for the population could be within. And so it turns out that the formula for this population mean is this. So let me read this. This is population mean is equal to x bar, which is sample mean, plus or minus. Now we have a new symbol. Instead of a z, it's a t. And there's a right subscript of alpha divided by 2. And all this is one variable. And then multiplied by s divided by the square root of that. Okay, so let's do this from an example. Let's say that you gather a sample. Let's say 40 people. And you give each of the 40 people an IQ test. And after you get the IQ scores for all 40 people, you punch them in your calculator. The calculator will give you the mean and standard deviation for those 40 IQ scores. So let's say that the mean, and this is the mean of the sample, so this is going to be abbreviated by x bar. So the mean of the sample, let's say, is 102. And the standard deviation of the sample is, let's say, 14. And this represents IQ scores. Okay. So from this sample of 40 IQ scores, you want to know what the average IQ is for the whole country. So we're going to use this formula that represents a confidence interval for the population mean. And so let's put in the numbers. X bar is already given to you, that's 102. We're gonna get to this t-score later, after we fill in the other numbers. So the S will be 14, that's given. And then the N is the sample size, so that's given also at 40. So that'll be the square root of 40. The only thing left is this t-score. So let's talk about what that is. And let's say also the confidence level is given to you. Let's say the confidence level is also 95%. Okay, so in the previous formula, when you see z-score, you know that the underlying distribution for that variable is in the shape of a bell curve. So z-score is a test statistic for a bell curve. But if you see a t-score, we're dealing with a different distribution. So it turns out that This is what we call a t-distribution. And the shape is very similar to a bell curve. Symmetric on both sides. It reaches some maximum value somewhere in the middle. The only difference is that it's a little sharper in the peak. And we call this a t-distribution. This is going to have its own mathematical formula. It's not important to know the exact formula for the function of this t-distribution. But for now, it's just important to know that it's similar to a bell curve, a little sharper in the peak. So let me give you a little bit of background on this, put it into context. So the person who came up with this distribution was a mathematician in the late 1800s who was working for a beer company. He was working for Guinness. And his job was to model average beer production volumes in a six-pack container. So in each six-pack container, we wanted to find the average volume of beer in each six-pack. And so he found that if he was modeling the average or the mean volume of beer in a six-pack, using a bell curve, it turned out to not be accurate. It turned out that for a certain beer volume, the relative difference was different for another value of the volume of beer in a six-pack. So these two were not, in the experiment, they were not getting the same relative differences that you would expect from a bell curve. So he came up with his own distribution, and he found out that this distribution modeled the average beer volume in a six-pack really well. And he was really excited about this, and he wanted to share it and publish it with the world. But he was working for a private company, and it was proprietary, and they forbid him to publish his results. So in the name of science, he did it anyway. But he called himself a fake name, called himself a student. So to this day, this is also called a student distribution. Even though this distribution has nothing to do with students or teachers or academics or anything like that. But because he arbitrarily chose to call himself student, this is called a student distribution. So student distribution is also called a t-distribution. Some of you guys might be wondering, well, why is it now called an S distribution instead of a t-distribution? S for student. And your guess is as good as mine, but my guess is basically S is already a variable in statistics. S is the sample standard deviation. So therefore, instead of the first variable in student being used, the last letter in student is used. So student distribution or t-distribution. Any questions? So just like with the z-score or the normal distribution having its own table, the t-distribution will have its own table. So let's talk about that table together. Okay, so you can find this table in multiple places, but one of the easiest places is the very back pages of the book, second to last page. Will be this chart that says table A3, T distribution, critical T values. So the way this chart is gonna work, put it here so the video can see. The way this table is gonna work is, first of all, there's gonna be degrees of freedom that's asked for. So the degrees of freedom is the sample size n minus the number of variables. But in this case, we've been doing one variable statistics. All these values in the distribution represent values of one single variable. So the number of variables will be 1, so the degrees of freedom will be n minus 1. So n is the sample size, so in our case, the sample size is 40, so the degrees of freedom, or n minus 1, will be 39. So then we're going to go to the first column, which is 39. I'll change projector in a little bit. We'll go all the way down to 39, and then once we get down to 39, the next column will say area in one tail or area in two tails. So let's talk about what that means. So if you have this T distribution, again, the confidence level here, 95%, has to do with the area around the distribution that's around the mean. So it has to do with this middle area given by the confidence level of 95%. That means if there's these two extreme areas, either too high or too low left over, that we've been calling the tails, so the two tails combined add up to how much, if our confidence level is 95%?
5%.
Yeah, 5% left over. That's if you're looking at both tails together. If you're only looking at one tail at a time, each tail individually should be how much? Yeah, half of 5%, which is 2.5%. So both tails together is 5%, one tail is 2.5%. So if you look at this chart, you'll see this label here, area in one tail on top versus area in two tails here. So you can use either one as long as you use the right number that corresponds to it. So if you use area in two tails, then use 5%. If you use area in one tail, then use 2.5%. So area in one tail will be 2.5% or 0.025. That's this center column here. And you notice in the exact same column, you see area in two tails, which is 0.05. So we're going to use that center column with area in two tails 5%, area in one tail half of that, and then we're going to go down to the correct degrees of freedom, which is 39. So we're using the center column, then we're going to go down to the correct degrees of freedom. In this case, it'll be 39. So go to 39 and then go to the center column, ends up being 2.023. So the number that we want from the chart is 2.023. And again, to use the chart, go to the right degrees of freedom, which is n minus 1, and then go over to the correct column, and you can use either area in two tails or area in one tail. And these are based on the confidence level that's given to you. Area in two tails is the total area left over for 100%. Area in one tail is half of that. Any questions? And then what was the number we got from the chart?
The number we got from the chart was 2.023.
Okay, great. 2.023. So that'll be the t-score that we use in our formula. So that'll be 2.023
two, is that covering all of this? Or is it just the T-scores? So we're finding the T-score by the degrees of freedom and then applying it by the chart and putting it in, so we don't have to divide something out or.
So every chart has its own convention. The convention of this chart happens to be, needs to know the area in either one tail or two tails in order to use the chart.
Will the questions define whether we need one or both tails?
No, later on, there's gonna be a reason for that distinction, but right now, when we talk about confidence intervals, you can use either one. Okay. Alright, so now that we use the chart to get this t-score, now we have all the numbers we need to calculate this resulting confidence interval. So again, there's going to be a quantity after the plus or minus, and we can call them the margin of error. So let's calculate this number after the plus or minus, or the margin of error first.
4.4781.
4.4781. So we're going to get a resulting confidence interval. What's the lower bound?
97.521.
0.152? 0.521?
5218 if you want to include the fourth.
Okay, thanks. And then that's the lower bound. What's the upper bound?
106.4781.
Okay, so what does this mean? This means that based on this one sample of 40 people having their average IQ score be 102, now we're trying to make a conclusion about the whole population, or the whole country in this case, that their average IQ will be somewhere between 97.5 and 106.4, and that will be true 95% of the time. So we're able to make a conclusion about the average IQ for the whole country based on only these 40 people. But notice the margin of error is pretty high, because it's only 40 people. Any questions? So just like before, in the previous case, where we're estimating the true proportion of success in the population, just like before, oftentimes there's a certain margin of error that we desire. So for example, instead of a margin of error of 4.4 IQ points in either direction, let's say we only want a margin of error of 1 IQ point in either direction. So the question is, how do we bring that margin of error from 4 down to 1?
We have to find the ideal sample size using 1%.
Okay, very good. So just like we said before, if we want to bring down the margin of error, we have to bring up the sample size. We have to look at a greater sample of people. So now the question is, just how big of a sample size do we need for this desired margin of error of 1 instead of 4? So just like before, we're going to take this entire margin of error expression and set it to what we desire, which is 1, and then solve for n. So let's do that. So the margin of error here, we want to be 1. And notice that we're trying to estimate the true mean IQ, and we're trying to find the margin of error being 1 IQ point in either direction. So this 1 represents 1 IQ point as an error, as opposed to representing a proportion or percentage. So before, we wanted a margin of error of only 1% in either direction. That's why we were using 0.01 or 1%. But this 1 represents not a percent, but an actual IQ point. So we're just using the number 1. Again, because we're trying to estimate a mean value, and the margin of error is only 1 IQ point, versus before we're estimating a decimal proportion or a percentage, and that's why when we said we only wanted 1% error, we've been using 1% or 0.01. So here we want a margin of error of only 1 IQ point. And so the error expression is everything after the plus or minus. So that'll be the t So we're trying to solve for n, the minimum sample size needed. So let's plug in what we know and solve for what we don't know. So the t-score from our table was 2.023. Or let's go ahead and just solve for n in terms of the variables. We don't have to plug in the numbers. And then 1 will be the margin of error. So we're trying to solve for n, assuming we have everything else. So how do we solve for n here?
Multiply both sides by the p-value?
Uh,
Or divide both sides?
Yeah, good. So right now the t-value is being multiplied, so let's divide both sides, undo that. Both sides. So dividing both sides by t. Gives us that. So what's the next step we could take to solve for n?
Divide both sides by s?
Yeah, we can divide both sides by s, and if we do that, what do we end up with the left?
1 over n.
Yeah, okay. Divide both sides by s to get 1 over square root of n on the left. Okay, what's the next step we could take? So right now, the things that are preventing n from being by itself is that there's a square root stuck to it, and also it's on the bottom of the fraction. So how do you undo one of those two things?
Multiply both sides by square root of n over square root of n.
Okay, good. So if you're doing the same thing to both sides, you can just multiply by the square root of n.
Okay.
It doesn't have to be 1.
Okay.
So let's just multiply the square root of n to both sides. So then we're going to get 1 square root of n times 1 divided by the square root of n is just 1. So we're going to multiply both sides with the square root of n. And wanna solve for just n. So what now?
Divide both sides by e, and then multiply both sides by the t-value and s.
Very good. So essentially, we can isolate just the square root of n by dividing both sides by this number that's being multiplied by the square root of n.
Right.
So, dividing by a number is the same as multiplying by its reciprocal. So, the number is currently this ratio, so multiply both sides by the reciprocal or the number flipped. So we're gonna multiply both sides by the reciprocal of this number, essentially dividing by that number. So we have 1 multiplied by the reciprocal. Over E. So on the right, the result of multiplying the reciprocal, you're just gonna get 1, and then times the square root of it. So then, we're almost there, but instead of having just n by itself, we have the square root of n. So how do we get n by itself?
Square both sides.
Square both sides. So we're gonna square both sides. Up here, 1 times anything is itself, so we can just ignore the 1 here. So this will be t. So we're gonna square both sides. So n, the sample size needed, will be whatever the t-score is times s divided by the magnitude of error that you desire, all squared. So you can either leave the whole thing as being squared, or because the argument inside the squared is all multiplication and division, you can distribute the square term across the square operation across every single term. So this is the same thing as t alpha over 2 squared times s squared divided by e squared. So either one is fine. So let's go ahead and do that for this particular example. So the t-score that we got from the chart was 2.023. The s squared is the 14 squared. And the e is, in this case, just one IQ point. So to find this n, take 2.023, square it, and then times 14 squared.
So it'd be 803.
Okay, good. So that means that if you want to find the average IQ for the whole country within only a margin of error of 1 IQ point in either direction, you only need 800 people, 800 something people.
You can't have a portion of a person, so you go to the next one.
So you would always round to the next one. Very good. So what would be the exact answer then?
It'd be 803.
803. Good. So the sample size you need here is going to be 803. It was 802 point something, but again, you can't have a decimal person, so to be safe, you always round to the next number. Alright, any questions? Okay, so what we did today is we reviewed the idea of confidence interval. You're trying to estimate some true number for the population. And in particular, we reviewed a population proportion success, the formula we talked about last time, and then we talked about a new formula today to find estimating the population mean, and that has its own formula, which involves this new t-score, which is a table that we just talked about. Okay, any questions? All right, that's it, guys. Have a good day.
much, probability do we have on our exam that we can walk through and convert from a five-step process to find an answer?
Oh,
in
this-
an equation?
This formula for n, will be already in your book, and it's derived exactly this way. So once we've already derived it once, we know what it means. Once we can just use the one that's already in your book. That'll give us exactly. We won't have to derive it again. Okay.
No, it's, so I remember taking another rule where it's like, you know, hey, here's a problem, now figure out how to convert it for this. And you have to go through this to shift it over and do this whole process so you can actually solve it. Are we gonna be doing something similar like that? Or is it mostly like, here's your data, figure out what you need, and you're like,
Probably not. So probably it'll just be using this formula that's already derived for you, and this formula that's already given to you.
okay. I'm trying to be clear on my words, because I understand how vital that is in statistics.
Yeah.
And I had a really good example that made me stop and think, and this little girl was just like, how did I miss that? You know, 30 cows in the field, 28 chickens, how many did? I didn't realize it's not 28, it's 20 cows, 8 chickens, so 10. I'm like, I
Okay.
hate you right now. But yeah.
Yeah, so I think like last week, at the end of the week, if like we could use notes.
Oh,
And I just wanted to see if like.
Yeah, let me,
the conclusion of that.
let me consider it a little more and I'll let you know.
Okay.
Yeah.
Yeah, before the test.
Sure.
Okay.
Okay.
I would not erase the board yet.
Okay.